All right, this is Mr. Yeager for Honors Chem, and we are finishing up our enthalpy section here, which I know has gone very long. And we're looking at what's called Hess's Law. We're looking now at basically finding enthalpies of reactions, of actual chemical reactions. So I am going to kind of go over the basics here and then show you examples so you can see me use all these steps. So Hess's Law is a way of basically determining the energy that is released or absorbed in a chemical reaction based on what's called the heat of formation of the compounds of the reactants and products. So what the heck does that mean? The idea is during a chemical reaction, we have to obviously break certain chemical bonds of certain elements and then reform them with other elements. And so what happens here is you're going to see in a moment, to actually do this process, you need to actually see multiple chemical reactions. The idea of what is the energy to break a carbon dioxide molecule into carbon and oxygen? What is the energy then to form a carbon and carbon and oxygen, I said. What would then be the energy of forming a bond between carbon and sulfur? That would be a separate reaction in a way, okay? So while we see a chemical reaction as like one line, as one chemical equation, there are multiple pieces and bonds breaking and reforming during this process, and we have to add up and subtract all of those energies that are being absorbed or released in that process, and that's what Hess's Law is looking at. So what we basically do is you will be given the final chemical reaction you are trying to find the enthalpy for, okay? It'll say, hey, we want to find the enthalpy for this chemical reaction, okay? And most of the time it's already balanced for you. All right, it actually should be basically balanced for you. What then will happen, this is where it gets the confusing part, is you're given multiple other reactions with the enthalpies of those reactions that include some of the reactants and some of the products in your final chemical reaction. All right? And essentially, if I take this from an algebra perspective, it's like I have a system of equations is really what I'm looking at, which you might immediately go, oh no, all right? But this is like ones and twos you're basically adding together. But that's what you have, and we got to rearrange those equations. And when I say rearrange, there's two things that I can basically do to those reactions where after I then add all the pieces together and eliminate the same chemicals that show up on opposite sides, it should form the final overall reaction. All right? And again, you might need to wait to see an actual reaction take place that I do this, but that's what's going on here. All right? And so there's basically two steps you're going to take with these separate chemical reactions away from the final one that you want to make. You are basically going to do either flipping the reaction. In other words, what I mean by that is switch sides, switch the reactants and products to the opposite sides. And you will also need to balance the reactions by, in other words, you might have to multiply one of the 8 reactions by 2, 3. In some cases, this is going to be weird, you might even have to multiply by 1/2 or divide by 2, all right? So that when you officially add those two reactions together, you will get the identical final reaction that you're looking for, okay? So what happens when I flip or when I balance? When you flip or reverse the reaction, all you do is you change the sign on the enthalpy, just like we did when we did heat of fusion and heat of solid. Enthalpy of fusion, enthalpy of solid, where you just reverse the sign. You don't do anything other than change it from a positive 20 to a negative 20 if you have to reverse the reaction. If you have to increase or decrease the coefficients by a certain factor, so if you increase everything by 2, you need to multiply the enthalpy by 2. You have to multiply or divide the enthalpy by that factor you change the reaction by. At the end, you then add all of those enthalpies up. If you again put your chemical reaction back together and everything is as it is, you simply just add all of those enthalpies up. Add/subtract, because again, they might be negative, but you add them all up. All right? So let's take a look at this. So I'm starting off with this one because this one is kind of as simple as they can really get in most ways. All right? So what I have here is the reaction I'm looking for is up top. basically we have a reaction where you can change solid carbon graphite into solid carbon diamond. Basically, you create multiple new bonds between the carbon atoms and they become a diamond. Obviously, graphite and diamond are essentially the same composition, just way more bonds between the carbons with the diamond. Okay? So you can see here, it says I have graphite plus oxygen produces carbon dioxide, all right? And that's already essentially a balanced equation, C, 1C, 1C, 2 O's, 2 O's. And this will have a heat of reaction, okay? They have C, it's sometimes called composition or standard, it actually is more of a standard enthalpy of formation, okay? And that's negative 394 kilojoules per mole. So if that reaction occurred, this is a very exothermic reaction, right? For diamond, it looks very similar, obviously same elements, just a different form of carbon. It has an enthalpy of negative 396 kilojoules per mole. So what I basically have to see here is graphite is on the reactant side of my final chemical reaction. Diamond is on the product side. So the first thing I really need to do is I need to reverse this bottom reaction. I just need to flip it. So I'm going to change it to CO2 produces C diamond plus O2. And when I do that, that causes the sign to now be positive for that particular enthalpy. If I flip the reaction, it flips the sign. So this reaction at the bottom is positive 396 kilojoules per mole. From there, I don't need to do any sort of factor changes. I'm not going to reverse the first reaction because graphite's already in the reactant side. And so what basically happens, I'm going to cross out this middle one, is essentially I add these two chemical reactions up together. So if I write it all out, and again, I don't feel like you have to do this every single time, but I write everything that's in the reactant side. It's like almost like a net ionic equation thing. You add all the reactants, so graphite, oxygen, and CO2 from the second reaction will produce C diamond plus O2 plus CO2. And whatever is on either side, the same, I have to cancel out, again, equally. So I have one oxygen on the reactant side, one reaction on the product, oxygen on the product side, so they cancel out. I have one carbon dioxide on the reactant, one carbon dioxide on the product. So now I have my final reaction. And ultimately, again, what was I doing? I wanted to figure out what would be the enthalpy of this reaction. Well, now all I have to do is just add these two numbers up. I didn't have to do anything to my first enthalpy. I didn't flip it. I didn't change the factor in the equation on it. I did flip the second one, so I changed the sign. So this would simply be negative 394 plus 396. The answer is positive 2 kilojoules per mole would be the enthalpy of the reaction. That's Hess's law. Okay? All right, let's do another one. Okay, so this one is saying calculate the heat of formation for sulfur dioxide from its elements. Okay? So in other words, I want the formation of sulfur dioxide, which means sulfur dioxide has to be on the product side. All right? And it doesn't necessarily give us the final chemical equation. We're going to be able to kind of see this in a minute. Okay, we'll see how this works out. Most of the time we're given the chemical equation, so this one might be considered a little bit more difficult. But it says the heat of formation from its elements. So in other words, I'm basically saying I want S plus O in some form to form SO2. That's essentially what I'm trying to say. Okay? And it says we can just say S is sulfur. We don't need S8 or S4 or all the different kinds. So if I look at my reactions, I look at this and I see sulfur, I see sulfur already in my reactant side. So that means I don't want to do anything with the first reaction yet. I want to keep that one. But I have sulfur dioxide in the reactant side and I need that on the product side. So I do need to reverse the second equation. So 2SO3 will produce 2SO2 plus O2. And what does that do? It changes the sign of the enthalpy to a positive number. So the second one is now positive, a positive 198.2. Okay, 198.2. All right, the thing is here, I need to cancel out this SO3. This SO3 is not in my chemical reaction. How do I know? It says I'm doing a formation of sulfur dioxide from the elements. So I can only have sulfur and oxygen, and this would be O2 in the end, it would be, in my final reaction on the reactant side. So what this is where I kind of look at this. I go, okay, I have two SO3s here. I go back to my first equation, I have only one SO3. So what am I going to do? I'm going to multiply this whole top reaction by 2. That'll give me two SO3s there. That would basically do 3/2 times 2 would become just 3. And then I'd have two S's. So my reaction for the first one would be 2S plus 3O2 produces 2SO3. And again, why am I doing that? I need to cancel it out. I need two SO3s to show up on the reactant and the product side so they can be canceled out on both sides. So I multiplied the whole first reaction by 2, which means I need to multiply the first enthalpy by 2 in the end. And again, now you can see what's going to happen here. A lot of times when I do this, I kind of cancel out along the way. The SO3s are going to cancel out. I have one O2 on this side, so this is going to go down to just 2. And there's my final reaction. 2S plus 2O2 forms 2SO2. And it's balanced. 2 S's, 2 S's, 4 O's, 4 O's. But what's my enthalpy going to be? My enthalpy of reaction, based on all the things I did, is going to be 2 times negative 395.2 plus 198.2. And that should come out to, I have it as negative 592.2 kilojoules per mole. So that's showing you the two different things you can basically do to your reactions, where you can multiply your enthalpy by the factor you change it by, and you can change the sign by flipping the reaction around. One more. So this one I want to do because you can see you have 3 reactions. That's fine. We might have to try to figure out how all 3 of these to go together. But it does give me the initial reaction, which is good. So I have N2O plus NO2 forming 3NO. So I need N2O, NO2 on the left-hand side in the end. Again, it could show up on both sides, but it has to cancel out where I only have one on the left side. And then I need 3 NOs on the product side. 3 NOs on the product side. Okay? So let's see what I can kind of mess around with here. All right, I think this one is actually kind of difficult if you remember going back and looking at this one. So I need NOs on the product side, I believe, for the most part. I think that's what I'm looking for. All right, but I only want 3. Yep, okay, I think I remember where we're going with it. So I don't think I'm going to do anything to this first reaction. I'm going to leave it as is so that enthalpy doesn't change. I'm going to reverse the second reaction. I'm going to change it to 2NO2 forming 2NO. Let me do this. Let me pull down the first reaction. N2 plus O2 forms 2NO. And I'm going to reverse the second one. So 2NO2 forming 2NO plus O2. Okay? All right. And then the last one, I'm going to leave as is for the moment because that's the only one that has the N2O in it. So I don't think I'm going to have to reverse this last one. The thing is, if I add this all up, I have too much stuff. Okay, I have too many things happening here. I'll have leftover compounds because I don't want N2 and O2 left over either. I want them completely canceled out. So the way I look at this is 2 things. Essentially, what I see happening here, okay, sorry, I did do this. I do need to make sure. I did reverse the second reaction, so that's now positive. I do need to make sure I remember doing that. So I did change the sign on the second reaction. But I need only one more NO. So maybe I multiply this whole reaction by 1/2. And again, you saw on the prior equation, we will get weird things like 3/2 and 1/2 and stuff like that. While again, I've always said you never use those in balancing reactions, they are used in creating these heat of formation problems. So that's kind of weird. I know you're like, why? But we're allowed to go ahead and now multiply by halves and things like that as needed for these problems. So if I multiply everything by 1/2 in this, that means I need to multiply this reaction by 1/2. Watch what happens. I'm going to go down to 1 NO2 there. I'll have only 1 NO here, and I'll have a half of oxygen there. So that will give me my 3 NOs. So I'm good there, but I only need 1 NO2. So guess what? I'm going to do the same thing with this one down here. I'm going to multiply everything by 1/2. So I'm going to multiply this last heat of formation by 1/2. And so that would lead me to having only 1 NO there, only 1 N and a half of O2. And watch what happens here. I now have only 1 N2 and 1 N2 on both sides, so they cancel out. I have 1 O2 and 1/2 plus 1/2 is 1, so all the O2s cancel out. And now I got it. N2O plus NO2 produces 2 plus 1 is 3 NOs. And I have my chemical reaction. So now what do I have to do with all my heat of formations? I need to add them up and do everything that I changed the reaction with. 180.7 plus 113.1 times 1/2 plus negative 163.2 times 1/2. And I believe that comes out nicely to 150, wait a minute. I think I might have made a mistake on this real quick. 155. Yep, I think I forgot a negative sign. It would be 180.7, because I didn't flip around the first one, plus 113.1 times 0.5 plus negative 163.2 times 0.5 is 155.65 kilojoules per mole. Okay. 155.65 kilojoules per mole. And there you go. That's Hess's law. So again, gotta take some time to practice through it. I think after you do a couple, you kind of keep on seeing the trends that occur. You usually don't do anything that crazy. It's not like we're going to flip all 3 reactions around. I mean, I guess you could, but you know, follow the rules of how it goes and move along from there. All right. Thank you very much.